Welcome to class number 2, session number 1. In this class, we will see how scientists see what's going on the extremely small world of nanotechnology. The microscopes that are typically used in high schools or colleges will not do the job. Therefore, nanoscientists use high-powered microscopes that use unique methods to allow them to see the surface features on the atomic scale. This way, the scientists effectively open the door to the modern nanotechnology. The first tool we will learn about in this session is called atomic force microscopy, or abbreviated as AFM, or scanning force microscopy, which abbreviated as SFM, which are basically very high resolution type of scanning probe microscopy. This type of microscopy demonstrates a resolution on the order of fractions of a nanometer, more than 1,000 times better than the optical diffraction limit. The information in the AFM is gathered by feeling the surface with mechanical probe. In this context, piezoelectric elements that facilitate accurate and precise tiny movements enable the very precise scanning on the surface. In some variations, electric potentials can also be scanned using conducting cantilevers. The AFM consists of a cantilever with a sharp tip or probe at the end that is used to scan the specimen surface. The cantilever is typically silicon or silicon nitride with a tip radius of curvature on the order of few nanometers only. When the tip is brought into proximity of a sample surface, forces between the tip and the sample lead to a deflection of the cantilever according to the Hooke's law. Depending on the situation, forces that are measured in AFM include mechanical contact force, van der Waals forces, capillary forces, chemical bonding, electrostatic forces, magnetic forces, solvation forces, etc., etc. Along with force, additional quantities may simultaneously be measured throughout the use of specialized types of probes. Typically, the deflection is measured using a laser spot reflected from the top surface of the cantilever into an array of photodiodes. Usually, the sample is mounted on a piezoelectric tube that can move the sample in the Z direction for maintaining a constant force. On the other hand, the X and the Y directions are used for scanning the sample. In alternative modes, a tripod configuration of these three piezoelectric crystals may be employed, with each responsible for scanning in the X, Y, and the Z directions. In newer designs, the tip is mounted on vertical piezo scanner, while the sample is being scanned in X and Y using another piezo block. The resulting map that represents the topography of the sample can be then achieved. Advanced AFM tools can reach lateral resolution of 0.1 nanometer and a vertical resolution of 0.02 nanometers, more or less. The AFM tool can be operated in a number of modes, depending on the application. In general, possible imaging modes are divided into static, also called contact modes, and a variety of dynamic modes, usually called non-contact or trapping modes. And in these cases, the cantilever is not in contact with the device, but rather is vibrated, as we will explain later on. In the static mode operation, the static tip deflection is used as a feedback signal. Because the measurement of the static signal is prone to noise and drift, low stiffness cantilevers are used to boost the deflection signal. However, close to the surface of the sample, attractive forces can be quite strong, causing the tip to snap in to the surface. Thus, static mode AFM is almost always done in contact where the overall force is repulsive. Consequently, this technique is typically called contact mode. In the contact mode, the force between the tip and the surface is kept constant during the scanning by manipulating a constant deflection. Of course, for every technique has its own pros and cons. Right now, we will show what are the advantages and the disadvantages of this approach in the AFM. Amongst the rest of the advantages of this approach, namely the contact mode, we shall mention the fast scanning, good for rough samples, and the ability to use this approach for friction analysis. On the other hand, the disadvantages include the fact that the forces can damage or deform soft samples, and therefore they cannot usually be utilized for these samples in most cases. The second mode is called the non-contact mode. In the non-contact mode of the AFM, the tip of the cantilever does not contact the sample surface. The cantilever is instead oscillated at either its resonant frequency or just above the frequency, where the amplitude of the oscillation is typically a few nanometers, usually less than 10 nanometers, and down to few picometers. The van der Waals forces, which are strongest from 1 nanometer to 10 nanometers above the surface, or any other long-range forces which extend above the surface, act to decrease the resonance frequency of the cantilever. This decrease in resonance frequency, combined with the feedback loop system, maintains a constant oscillation amplitude or frequency by adjusting the average tip to the surface distance. Measuring the tip to sample distance at each x and y coordination point allow the scanning software to conduct the topographic image of the sample surface. One of the main advantages of the non-contact mode is that it exerts very low force on the sample. This makes the non-contact mode AFM preferable for measuring soft materials such as biology sample or organic thin films. Another advantage of the non-contact mode AFM is the extended probe lifetime. Indeed, non-contact mode AFM does not suffer from tip or sample degradation effects that are sometimes observed after taking numerous scans with contact AFM. On the other hand, non-contact mode have also some disadvantages. A main disadvantage of the non-contact mode is generally lower resolution. If a few monolars of adsorbed fluid are lying on the surface of a rigid sample, the images may look quite different. However, in the case of rigid samples, contact and non-contact images may look the same. Additional disadvantage is that contaminant layer on the surface can interfere with oscillation, and that best imaging with non-contact mode usually need ultra-high vacuum or UHV conditions. An intermediate mode between the contact and non-contact FM is called tapping mode. In this mode of operation, the cantilever is oscillated at the resonant frequency. The probe lightly taps on the sample surface during scanning, contacting the surface at the bottom of its swing. By maintaining constant oscillation amplitude, a constant tip-sample interaction is maintained and an image of the surface is usually obtained. The advantages of this approach that it allows high resolution of samples that are easily damaged or loosely held to the surface. And of course, this approach is quite good for good and biological samples. Disadvantages include that this technique is more challenging to obtain an image in liquids, and of course make the speed of imaging a little bit slower. Following a video that demonstrates the AFM operation along with animated presentation.
The microscope's cantilever is activated to vibrate at resonance. As it is lowered, attractive forces between the tip and the sample alter the cantilever vibration. The cantilever returns to its unperturbed vibration when withdrawn from the sample. The set point for the cantilever vibration determines the distance between the tip and the sample for imaging. 2. Scanning principle. If the tip is scanned across the sample, the tip height is adjusted by feedback to keep the cantilever vibration at the set point and the distance between the tip and the sample constant. 3. Scanning the sample. As the tip is raster scanned across the sample, the tip height is adjusted to keep the cantilever vibration at the set point, and so the tip follows the topography of the sample. The height of the tip is recorded along with the coordinates of its point in the scan. The resulting map of tip position can then be processed to render an image of the sample topography with nanometer resolution.
One example of the AFM image for nanoscale materials could be seen in the uplift image for copper wire that have a Y shape. A round shape and a line diameter of 8 nanometers can be easily observed in this image. Another example is the AFM image of germanium network on silicon substrate. As seen in the image, the size of the islands as well as the separation between the adjacent islands is clearly observed, indicating the high resolution of the AFM. We will move now to the scanning electron microscope. The scanning electron microscope, which abbreviated also as SEM, uses a focused beam of high-energy electrons to generate a variety of signals at the surface of the solid specimens. The signals that derive from electron-sample interactions reveal information about the sample, including external morphology, chemical composition, and the crystalline structure and orientation of the material making up the sample. In most applications, data are controlled over a selected area of a surface of the sample, and a two-dimensional image is generated that displays spatial variations in these properties. In a typical SEM, an electron beam is thermoionically emitted from an electron gun, such as tungsten filament cathode. The electron beam, which typically has an energy ranging from 0.2 kV to 40 kV, is focused by 1 or 2 condenser lenses to spot about 0.4 nanometer to 5 nanometer in diameter. The beam passes throughout pairs of scanning coils or pairs of deflector plates in the electron columns, typically in the final lens, which deflects the beam in the X and Y axis so that it scans in raster fashion over a rectangular area of the sample surface. When the primary electron beam interacts with the sample, the electrons lose energy by repeated random scattering and absorption within the teardrop-shaped volume of the specimen known as the interaction volume, which extends usually from less than 100 nanometer to around 5,000 nanometers into the surface. The size of the interaction volume depends on the electron's landing energy, the atomic number of the specimen, and the specimen's density, of course. The energy exchange between the electron beam and the sample results in the deflection and reflection of the high energy electrons by elastic scattering, emission of secondary electrons by inelastic scattering, and the emission of electromagnetic radiation, each of which can be detected by the specialized detector. The beam current absorbed by the specimen can also be detected and used to create images of the distribution of specimen current. Electronic amplifiers of various types are used to amplify the signals, which are displayed as variations in brightness on a computer monitor. And each pixel of the computer is synchronized with the position of the beam on the specimen in the microscope, and therefore the result is image that is distributed map of the intensity of the signal being emitted from the scanned area of the specimen. SEM can achieve resolution better than 1 nanometer. Specimens can be observed in high vacuum, low vacuum, and in environmental SEM specimens can be observed also in wet conditions. Following a short video that demonstrates the SEM operation along with animated presentation. Please have a look and try to connect the parts described in the previous slide with the shown parts in the animated video. Enjoy. Transmission electron microscopy, which are abbreviated usually as TEM, is a microscopy technique that enables the instrument's user to examine fine details, even as small as a single column of atoms, which is tens of thousands times smaller than the smallest resorbable object in a light microscope. TEM forms a major analysis method in a range of scientific fields in both physical and biological surfaces and sciences. TEMs find applications in cancer research, virology, material science, as well as pollution, nanotechnology, and semiconductor research, and of course, in the current lecture, we will focus on nanotechnology. There are 4 main components to a TEM: an optical column, or more specifically, electron-optical column, a vacuum system, the electronics, and the control software. A modern TEM typically comprises an operating console supported by a vertical column and containing the vacuum system and control panels for the operator. The microscope may be fully enclosed to reduce interference from the environment sources and operated remotely. The electron column includes elements similar to those in the light microscope. The light source of the light microscope is replaced in the TEM by electron gun, which is built into column. The glass lenses are replaced by electromagnetic lenses. Unlike glass lenses, the power of magnetic lenses can be changed by changing the current throughout the lens coil. The eyepiece is replaced by a fluorescent screen or digital camera. The electron beam emerges from the electron gun and passes throughout the specimen, transmitting electrons which are collected, focused, and projected onto a viewing device at the bottom of the column. The entire electron path from gun to the camera must be always under vacuum, or more specifically under ultra-high vacuum. Resolution of the TEM is limited primarily by spherical aberration, but the new generation of the aberration correctors have been able to partially overcome spherical aberration to increase resolution. Hardware correction of spherical aberration for high-resolution transmission electron microscopy, which abbreviated usually HRTEM, has allowed the production of images with the resolution below 0.5 angstroms, or 50 picometers, and magnifications above 50 million times. The ability to determine the positions of the atoms within materials has made the HRTEM an important tool for the nanotechnology research and development. Still, there are a number of drawbacks to the TEM technique. Many materials require extensive sample preparation to produce sample thin enough to be electron transparent, which makes the TEM analysis a relatively time-consuming process with a low throw-out samples. The structure of the sample may also be changed during the preparation process. Also, the field of the view is relatively small, raising the possibility that the region analyzed may not be characteristic of the whole sample. There is a potential that the sample may be damaged by the electron beam, particularly in the case of biological materials. In this slide, you will see a short video that demonstrates the TEM operation along with animated presentation. Enjoy.
At the top of the Titan column is the highly stable, reliable, high-brightness electron source, the XFEG Schottky emitter. The XFEG electron gun delivers high coherence and brightness that is coupled with high emission stability to produce stable measurement conditions not just for hours, but greater than 1% emission current stability over a week-long period of operational use. The extreme high brightness offers high beam currents in atom-sized probes for the acquisition of fast and reliable atomic images and chemical maps. Below the electron source is the monochromator, which narrows the energy spread of the electron source down to as low as 100 millielectron volts. This boosts the lateral resolution in high-resolution TEM imaging to 70 picometers and enables the spectroscopic study of electronic structures, as shown here in this sample of germanium-112 resolved to 80 picometers. In plasmonics, as shown in this visualization of plasmon structures of silver nanoantennas, and in chemical bonding, as shown in this atomic resolution oxidation state analysis on Syria catalyst surfaces. Beyond the monochromator is the accelerator, with the broadest commercially available acceleration voltage range of 60 to 300 kilovolts. The accelerator's voltage range provides unprecedented performance on any material in terms of penetration power for dense material, high contrast for light compounds, and in minimizing knock-on damage of beam-sensitive samples. This technology, in combination with CS correctors for STEM, delivers unprecedented atomic resolution performance for structural research across the entire acceleration voltage range of 60 to 300 kilovolts. Here you can see the atomic resolution is preserved across the acceleration voltage range, shown in the atomic images of gold acquired at different voltages. Young's fringe experiments show the stability of the deep sub-angstrom information transfer across the acceleration voltage range. The 3-lens condenser zoom system controlled by smart optics is optimized for a large range of parallel illumination in TEM mode from nanometers to micrometers. The range in convergence angles is extremely broad for focused probe mode applications, from ultra-small angles in nanobeam diffraction applications used in strain measurements to large convergence angles in CS-corrected HR stem imaging or convergent beam electron diffraction seabed applications for structural research. The D-Core probe CS corrector enables extreme high probe currents in atomic-sized probes for atomic chemical mapping and deep sub-angstrom stem imaging in bright and dark field applications. Atomic resolution imaging and chemical mapping across the large high-tension range of the Titan is achievable with optimum results for different materials with this technology. 63 picometers can be resolved in the high-angle annular dark field stem detector imaging of gallium nitride in 211 projection with an extremely high energy resolution of 130 millivolts. By using the Team Project microscopes, even the germanium dumbbell with a spacing of 49 picometers can be resolved using HR stem. In combination with an EEL spectrometer or Super X detector, atomic chemical mapping reveals the polarity of gallium arsenide or the chemical change at perovskite interfaces. The Super Twin lens has a large pole piece gap of 5 millimeters. This allows for a large tilt range of the specimen. This range is important to orient polycrystalline specimens in the desired projection, so that the structure can be determined in 3 dimensions as illustrated in the atomic resolution images of germanium in different projections. In complex multi-composite materials, the high tilt range of up to 70 degrees enables 3D imaging with tomography techniques. This powerful combination of unique technologies in one platform is now complemented with the ultimate spectrometer for low-concentration chemical analysis, atomic resolution chemical mapping, and 3D chemical mapping, the Super X detector, which is part of the FEI patented ChemiStem technology. The symmetric design of 4 detectors around the sample increases the collection efficiency and allows for flexibility in tilt without losing the EDS signal. In combination with the probe CS corrector, the Super X detector enables atomic chemical mapping, as shown in the example of gallium arsenide in 110 projection. The polarity of the structure can be visualized by the additional information of the different chemical content of the dumbbell structure. Even the difference in chemical composition between mixed and pure atomic columns can be detected as shown in this example of yttrium titanate. The image CS corrector boosts the resolution of the HR10 mode to the sub-angstrom level. It minimizes the effect of delocalization in HR10 imaging, which enables one to determine atomic coordinations at interfaces artifact-free. At 300 kilovolts, interstitial atoms can be visualized in germanium crystals to get a better understanding of point defects in these materials. At low voltage, focal series reconstruction on graphene double sheets allows one to obtain both 2D and 3D atomic resolution. The projector system is ultra-stable due to its constant power electronics and offers a maximum range of magnifications for imaging and large range in camera length for diffraction and EELS applications, maximizing the collection angles for high sensitivity. The system is not only designed to perform at extremely high magnifications for atomic imaging or spectroscopy applications, as shown before, but the special post-column energy filter lens series enables one to acquire high-contrast, zero-loss filter diffraction patterns, large-angle convergence beam electron diffraction patterns, or extremely low magnification images in chemical mapping in energy-filtered TEM of entire lamellas produced by focused ion beam sample preparation.
With this video, we come now to the end of class number 2, session number 1. Thank you.